A linear transformation is a function from Rn to Rm such that satisfy these two conditions. First, have to separate additions. I mean, if we transform the addition of two vectors, should be the same that if we transform one, transform the other, and then perform the addition in Rm. And it should satisfy that the multiplication by scalars satisfy that if we multiply the vector by a number and then do the transformation, should be the same that if we do the transformation of the vector and then multiply it by a number. That in general does not happen, but if the map is a linear transformation, these two conditions have to be satisfied for any vectors, u and v, and for any number that we put there. For example, let's think on this particular function. This is a function that goes from R3 to R2, meaning that takes a vector in R3 and transforms it in a vector in R2, in this case, in this particular vector in R2. So let's investigate if this transformation is really a linear transformation. We have to check if every time that we do an addition, it really separates the addition, and every time that we multiply by a number, it really the number goes out of the transformation. So to do that, we are going to calculate the addition of vectors. So this has to be for any two vectors in R3. So let's put two generic vectors in R3. So for instance, x, y, z, and x prime, y prime, z prime. And so we are going to calculate, for one hand, t of the addition. I mean, u plus b. Right, let's call it this one u and this one b. So we are going to have to do the addition then first. Let's write this equal t of the addition. The addition of these two vectors is x plus x prime, y plus y prime, and z plus z prime. And now we have to apply the transformation to this vector in R3. The transformation means this transformation, right, that we can read as to any x, y, and z, what it does. Well, the first component is 2 times x minus y. I mean, 2 times the first one minus the second one. And the second one is the first plus the third, right? So this plus this. So let's apply then this rule. So that will be 2 times the first one. The first one in this case is x plus x prime minus the second one. The second one is y plus y prime. Okay, so that's the first component. And the second component, according to this, is x plus z. I mean, x plus z. So let's add these two things. This is our x plus our z. Okay, so this is the result of the transformation by doing t of u plus v. We can simplify this to see clearly what the operation is. Let's expand this operation here. This will be 2x plus 2x prime minus y prime, comma, x plus x prime plus z plus z prime. Okay, so this is then the transformation, this part, let's say. So we know how much is t applied to the addition. Now let's see how much is this in order to check if they are equal or not. So that means that we have to do t of u and separately t of v and then add them. Well, t of u is t applied here. So this is simple, 2x minus y, x plus z, plus t applied at v, so that will be 2x prime minus y prime, comma, x prime plus z prime. Okay, so that is then t of u plus t of b. Let's perform this operation with vectors, the addition of these two vectors. This is 2x minus y plus 2x prime minus y prime, and comma x plus z plus x prime plus z prime, right? This one here. Okay, and so now the question is, are these two things equal? So let's check, is this really equal to this? 2x minus y minus 2x prime minus y prime. Yeah, it's exactly the same. And here x is here, z is here, x prime and z prime. So they are exactly the same. So these ones are equal. So the first condition for this one is satisfied. T of the addition is the addition of the transformation. Now we will need to check the second one, that the multiplication by a number holds. So let's calculate t of certain number a times u. So remember that u is this one, so we are doing then t of a times x, y, z. Multiplication of vectors, you know that this is ax, ay, az. And now we need to apply the transformation t to this vector. Let's read again what the transformation does. Is 2 times the x, in this case will be ax, minus y, y is ay, comma, x plus z, x plus z. So we'll write here then ax plus az. Okay, so we did the transformation in a times u. So now we have to do this other operation and see if they are the same. This other operation is to do a times t transforming u. So this is equal to a times t of u is simple. T applied here. So this is 2x minus y, comma, x plus z. So by multiplying now, we will have that this is a times 2x minus y, comma, a times x plus z. Let's perform this distributive here. That will be 2ax minus ay, comma, ax plus az. And now we compare. So we check that these two things that we obtain here and here are really the same. Well, we can see this first component is exactly this, and the last one is exactly this. So this means then that this transformation from R3 to R2 with this formula is really a linear transformation. We can see that, in this example it is, but we can see that that's not necessary, right? There are transformations, there are functions between, let's consider, for instance, this function t from R2 to R2. And let's consider a transformation that to each xy, transform it in x squared minus y, for instance. And so let's try to prove that this is a linear transformation. So as soon as we do here t of y, t of u plus b, that is in this case t of x plus x prime, y plus y prime, and following now this other transformation, we see that this equals x plus x prime square, comma, minus y plus y prime. So when we expand this, we see that this is x squared plus 2x x prime plus x prime square minus, in the second component, minus y minus y prime. So this is the result that we obtain as t of u plus b. Now, if we want to calculate now t of u plus t of b, we can see that t of u is simple x squared minus y, and t of b is x prime squared minus y prime squared. When we add them, we get that this is x squared plus x prime squared, comma, minus y prime. Sorry, here was not a square. Okay, so we can see now when we compare these two results that we obtain that this thing that we obtain here is really not equal to this one, right? So you see the second component coincide, but the first one not. So these are not equal. So in this case, t of u plus b is not equal to t of u plus t of b. So that means that this transformation that we have here is not a linear transformation. Okay, so it's a little tedious to prove, but it's needed to do the operations to see if something is a linear transformation or not. This is a very important result in linear algebra. Every time that we have a linear transformation, I mean something that does satisfy the conditions that I explained before, well, this is exactly the same that having a matrix such that T of V is A multiplied by V. So essentially, the linear transformations are the functions that are obtained by multiplying by a matrix. So if you have a matrix multiplied by a vector, the result of that is a linear transformation. I mean, it's a function that will satisfy the two conditions given before. In those cases, I mean, when we do have a linear transformation, the notation for that matrix that will exist always is this. I mean, if we have a certain transformation from Rn to Rm, so we're going to say that the matrix associated to this transformation is this one. So we are going to put some brackets around the name of the function, and that will mean the matrix. So in that way, we can say that T of B is the same thing that the matrix multiplied by B. So that will be the meaning of this notation. One very important characteristic of this matrix is that the dimensions of the matrix are this, is m times n, which means m is this number here and n this one. So that means that the matrix associated to the transformation is going to have m rows, right? So m is the number of rows of the matrix. So it's going to have as many rows as the dimension of the codomain. And the number of columns is going to be given by the number, by the dimension of the domain. Let's consider now this example of transformation. This is a transformation that goes from R2 and R3 and is given directly as a product of a matrix by a vector. Observe that the matrix has the correct dimensions, right? I mean, it's 3 times 2. I mean, has 3 rows and 2 columns. Okay, and so by given in this way, so this operation is given here, and we can see what is the result like this. So once that we have given the transformation as the multiplication by a matrix, we have actually the actual expression of the function as we have before. I mean, we can ignore this and set the transformation to each xy transformed in this directly. Okay, as we have given a transformation through the matrix, can be done also the other way around. I mean, we can start with a transformation like we have in our first example, like this one, and we will want to calculate the matrix because we know that it's completely equivalent to have a transformation or to have a matrix. So what will be the matrix associated to this transformation? Well, the idea is that the expression the expression of the matrix at any vector, remember that any vector can be written like this. I mean, where E1, E2, En are the standard unit vectors. The standard unit vectors are the ones that in R3 we were calling I, J, K. Well, in general, when it's n dimension, we can call E1, E2, E3, E4, E5, etc. But so, in any case, we know that any generic vector can be written as a linear combination of the standard ones. And then applying the conditions of linear transformation that we saw in the definition of a linear transformation, we know that all the additions are going to be separately, and all the numbers are going to be taken out of the transformation, because that is what a linear transformation is. So by doing that, we can have this expression, which is what that says actually that the value of the transformation is equal to just the component by the value in the standard unit vector, and so on with all the standard unit vectors. So in other words, all what you need is to know what is the transformation in the standard unit vectors, because then those will be just the columns of the matrix that after that, by doing the multiplication, will give us the general expression of the transformation. So, for instance, let's work in this example. In this example, we have that the general transformation is like this. But what is the matrix? The way to calculate the matrix then will be to calculate the image by the transformation of the standard unit vectors. I mean, like the 1, 0, 0. I mean, in whatever space we are, right? In this case, is in R3. So, will be what we would like to know is how much is this one, how much is this one, and how much is this other one. So by knowing those results, they will be just the columns of the associated matrix. So let's find out how much is by just applying the formula here, right? So 1, 0, 0 means the x is 1, the y is 0, and the z is 0. So we're going to have here 2 minus 0, comma 1 plus 0. So we're going to have here 2, 1. And so on, right? For the second one, then we will have minus 1, 0, and for the last one, we'll have 0, 1. So once that we have these three vectors, these are going to be just a column of the transformation. So the associated matrix 2T is going to be 2, 1, minus 1, 0, and 0, 1. So this is the matrix by putting each of these ones as columns in the matrix. Observe that this matrix has the required dimensions, right? This is a matrix that is 2 by 3. That is exactly what we want, right? 2 by 3. Remember, this is first and this is second always. Okay, so that's it. This is the way then to calculate the matrix associated to a transformation. And now, that's it. This is the result of calculating the matrix. But if you want to check that this thing is correct, actually you can pick this matrix. I mean, write this matrix 2 minus 1, 0, 1, 0, 1, and actually multiply by x, y, z, right? So by the vector that we have here, and check that the result that you obtained here, that should be a vector with two components, right? So check what is the vector that you get here. Of course, you should get this if the matrix is calculated correctly. You should be able to check that. Okay, so then we have a way to calculate the matrix associated to a transformation is we have here the actual expression of the transformation. So if we have a linear transformation, let's say for instance from R2 to R2, and we have given that this transformation at 1, 0, 1, 0 is transformed in the vector minus 1, 2, and 0, 1 is transformed in the vector phi 0. If we know that about this transformation, the question is, can we calculate how much is actually the transformation for any xy? Well, the idea is having the value of the transformation in the standard unit vectors, we can actually calculate the matrix. And once that we can calculate the matrix, then we can have the whole transformation. So we can write the matrix directly here from here. We have that the matrix is minus 1, 2, 5, 0. That's the matrix. And so how much is T xy? Well, let's just put here the matrix multiplied by xy. And so we're going, just by doing the multiplication here, we have that the result is minus x plus 5y, comma 2x. So the answer of the problem is then yes, the result of the transformation is t secant xy in minus x plus 5y 2x. But you see that in this case, in order to calculate the expression of the transformation, was very important to have how much is the transformation in the standard unit vectors. Well, sometimes we have how much is the transformation in some other base, not necessarily these standard vectors. In those cases, we also should be able to calculate the transformation. So, for instance, let's see this example. In this case, we have a linear transformation from R2 to R2, the transformation S, and what we know is that S to this vector is transformed in this, and this vector is transformed in this. But they don't tell us how much is S of 1, 0. That is what we would like to know, right? But still, even if we don't have that, we still can calculate that because we can try to put the vector 1, 0 in function of these vectors that we have given here and use the properties of the linear transformations to use the same procedure that before. So, for instance, 1 minus 1. So, well, we know that 1, 0, if we are able to write it as a linear combination of these two, so then we will be able to calculate the application because we know how much is the linear transformation in these two. Write down 1, 0 as a linear combination of these two, 1 minus 1 and minus 1, 2, right? So this one and this one. So let's write 1, 0 as a linear combination of these two. Let's just do the operations. 1, 0 should be equal to a minus b, comma, minus a plus 2b. And so from here, we have that a minus b have to be 1, and minus a plus 2b have to be 0. Let's solve this system of equations. Let's just, we can just add these equations here. So we have that b, 2b minus b equal 1. Well, substituting in any of them, we get that a is equal to. So we did find what is the linear combination here. So we know then that we can write 1, 0 as, instead of a and b, I'm going to put what I obtained. A is 2 and b is 1. And now we know that we want to calculate how much is s in this. So s on this. But now applying the properties of linear transformations, we know that this is 2 that gets out, s of 1 minus 1, plus 1 that gets out, s of minus 1, 2. And this one happen to be the ones that we have given, right? So that's why now we can put how much they are. And then this is 2 times 0, 3, plus just 1 minus 1. Then let's do the operations here. This is 2 times 0 is 0, 6 plus 1 minus 1. Let's add these two vectors and we get 0 plus 1 is 1 and 6 minus 1, 5. So we got that s at 1, 0 is 1, 5. So we know then that the first column of our matrix is going to be 1, 5. Well, in the same way, you do the same for the other one. So instead of 1, 0, you are going to do it for 0, 1. So you do all the same now for 0, 1. So all the same means you are going to write down 0, 1 as a combination, as a linear combination of the two same vectors. Let's say C times 1 minus 1 plus D times minus 1, 2. When you do the operations here, the same that we did before, we will get here C minus D minus C plus 2D. You put them equal to each other and you calculate then the result of the system, and you will get that from here C is equal 1, D is equal 1, 2. And so you have the numbers that you need there. And so S at 0, 1 will be equal to, here is a 1, so 1 times S of 1 minus 1 plus D is also a 1 times S of minus 1, 2. And these two are given here, right? So we have given these values here. So we can put directly 0, 3 plus 1 minus 1 in this case. And adding these vectors, we have here that this is 3 minus 1, 2. And then, by having the result of S 0, 1, 1, 2, we have the second column of the matrix. And so this is our matrix. Having the matrix, then you can calculate the expression of the transformation, right? So the expression for any xy is going to be equal to the matrix that we just calculate times xy. And now doing the operations, right? The operations with matrix. So that will give me the vector x plus y, comma, 5x plus 2y. And this is then the expression of the linear transformation when is given not in the unit vectors but in any other base. Okay, so if you are not sure if you did the operations correctly, you can check that this is correct. Once that you have the expression of the transformation, how would you check that this expression is correct? Well, you know that your transformation have to do this. Well, just check with your transformation, right? You calculated that Sxy equals x plus y, 5x plus 2y. So that's what you have now. So to know if this thing is correct, you can just plug in the values that you have given and see if you get the correct result. I mean to find out how much is this, for instance, by plugging in here. So if we obtain 0, 3, that is what it should be, right? If we don't obtain 0, 3, that there is something wrong. So let's plug in. The x is 1 and the y is minus 1. So then this is 1 minus 1, comma, 5, 1 plus 2 minus 1. So then this is 0, 5 minus 2 is 3. So that's what it should be. So it checks. Check with the other one and see also if you obtain what you should. Okay, so once that we understand what is a transformation, a linear transformation, we can talk about composing functions. If we have one linear transformation and then we have another linear transformation, we can apply one after the other. And then in that way we obtain the composition of the two. The only thing that is important to take care here is the order of the composition that is always sometimes feels that is not so natural. But the idea is that, let's see that we are starting Rn. So if we have, let's say, Rn here, and this transformation, T, goes to Rk, right? So that's what it says here. And this other one is starting Rk and goes to Rm. This is S. And so the composition should be a transformation that does the whole thing in one time. So this transformation here is the one that is called T composed with S. And you see how I am saying, right? I don't read here S, or I read it as T composed S. You start reading here T composed S. Because it's written that way because that's the order in which you do the operations, right? You apply first T and then you apply S. So that's the order in which you compose the functions. And so the composition SOT is starting Rn and finishing Rm. You see that it's always useful to do the diagram to understand the dimensions in the composition. In the same way, these matrices here have particular dimensions. So what this result says is that the matrix associated to this composition is the same that the matrix associated to S multiplied by the matrix associated to T. So this matrix you could calculate directly from the transformation. These ones you can calculate from the individual transformations, and then you do multiplication of matrices. So for instance, just looking individually, let's check the dimensions of these matrices. So if this is this transformation, the matrix T should be K times N. I mean K rows, right? And if this one S go from Rk to Rm, so this matrix should be M times K. And so observe that what we obtain here is exactly the case in which the multiplication is possible, right? So these two are the same, and the final answer, this matrix should be M times N. That when we look at here is what it should be. Okay, so be sure that you review all these dimensions and you understand exactly there is only with these dimensions the composition is possible. Composition is not always possible. It's possible only when the dimensions matches in this way. Let's do the composition of these two transformations, this one and this one. We could do it as simple composition of functions, and I would encourage you to try it that way. But we can also do a more simple by calculating the matrices. So we can calculate the matrix associated to each of these transformations. So let's calculate the matrix associated to S. So we look at the transformation here. Remember that to calculate the matrix is associated to this transformation. Remember that that is just to put as columns the image of the standard unit vectors. So we transform here 1, 0, and so then we obtain here 1, 5. If you observe, it's just the coefficients of x in here. And then for the second column, we transform 0, 1, so that will be just the coefficients of y, so that will be 1, 2. Okay, so that's the matrix S. And the matrix associated to T in the same way, so now we do the vector 1, 0, 0, the coefficients of x here will be 2, 1, and then 0, 1, 0, so the coefficients of y will be minus 1, 0. And then 0, 0, 1, the coefficient of z are 0, 1. So we have here the two, and you should be checking also the dimensions, right? You see that this dimension here, the dimension of this matrix, this is 2 by 2, because this is 2, 2. And the dimension here is 2 rows and 3 columns, because this is 2, 3. So every dimension check. And you should always do that check before keep going. Okay, so once that we have then the two matrices, so what is the matrix of the composition of this one of TOS? So the composition here has a matrix according to this that is simply the product of these two. So let's just multiply then these matrices. So let's check the multiplication is possible, right? I mean, it should be if we did all the dimensions correctly. But it is, right? Because this is 2 by 2 and this is 2 by 3. So this one is common, that's good. And the final answer is going to be 2 by 3. I mean, 2 columns and, 2 rows and 3 columns. Okay, so let's actually perform this multiplication. So this is going to be this times this. And so this is going to be 2 plus 1, this is 3, and then this times this, that this is minus 1, and so continues like this. So that will be here 5 times 2 is 10, plus 2 is 12, and then minus 5, and then 2. So this is the matrix of the composition. And so then if we actually want the expression of the composition, we just pick this matrix and multiply the matrix by x, y, and z, and we will get the expression of the transformation. So let's do that. So we don't need the matrices anymore. So now we need only the matrix of the composition that we calculate there. And so if we want to calculate now how much is T composed S applied to X, Y, Z, it's going to be just this matrix here. So I copy again this matrix, and I'm going to multiply this matrix just by X, Y, Z to get the general expression of the transformation. So this by x, y, z, and so this multiplied by this is going to give me the first element of the vector here. I will write it here. So that will be 3x minus y plus z. And now the second, this times this, that will give me 12x minus 5y plus 2z. So this is the composition then of the transformations S and T. Observe that this transformation goes from R3 to R2 as it should be, considering where these transformations go. So remember that we have in this case that T goes from R3 to R2, that's T, and then S goes from R2 to R2. So the composition should go from R3 to R2. Okay, so once we know compositions, we had the idea that when we compose two functions and we obtain the identity, so then we have that the function is has an inverse. So we're going to say that a linear transformation that goes from Rn to Rn, I mean that the two dimensions are the same. So a linear transformation from Rn to itself has an inverse transformation if and only if the matrix associated is an invertible matrix. And in this case, I mean, if this matrix is invertible, so we can say that the matrix associated to the inverse transformation is whatever matrix was associated to the transformation, but then the inverse, using the method of inverting matrices that you learned before. So, for example, let's consider this transformation S that goes from R2 to R2, and let's check first if this transformation has an inverse or not. So for that, we need to know if the matrix is invertible. Well, the matrix, we already have the matrix associated to this transformation is the matrix 1, 1, 5, 2. So to know if this matrix is invertible, remember that the condition for being invertible is that the determinant is not 0. So let's calculate the determinant of this matrix. And the determinant of this matrix is 2 minus 5, which is minus 3, which is not 0, right? So in particular, this matrix is invertible, and so we can say already that this transformation has an inverse. So S has an inverse transformation, and let's call it S to the minus 1, this inverse transformation. And what it does, this inverse transformation? Well, we know how to calculate the matrix, so if we calculate the matrix, we can also calculate what this function actually is doing. Okay, so let's calculate the matrix, which according to this is simple to calculate. I mean, the matrix associated to this will be the matrix associated to S, but then calculate the inverse. Okay? The matrix associated to S was this one. We will need to calculate the inverse of that. Well, the inverse of this matrix, and here you should apply, I mean, you have that the determinant is minus 3, you can calculate all the adjuncts, divide by the determinant, etc. And so the inverse matrix is this one. Everybody should be checking, should be stopping, calculating this inverse matrix. That is something that you know how to do. Okay, and so this is the inverse matrix. So having calculated then the matrix associated to the inverse transformation, we could say then that the inverse transformation takes an xy and does what? Well, multiply it by this matrix. So we just put here an xy, right? And we do the multiplication. By multiplying the inverse matrix by xy, we obtain that the expression is minus 2/3 x plus y over 3, 5/3 x minus y over 3. So then this is the expression of the inverse transformation.